Today we are talking about heaps, and this is a very important video because heaps are a fundamental data structure which we need to understand because they have very large applications in different algorithms and applications that we might use. So first off, I want to clear any confusion you may have. When you hear heap and you are probably used to programming in C, you might be thinking of, oh, are you talking about heap allocation, so malloc and free? No. Heaps in this case, which we're talking about, are binary heaps, or it's a data structure rather. So the heap that we allocate memory on, as in the memory kind of heap, that's a different thing from the heap data structure we're talking about. So just keep those two distinctions, keep that distinction in mind. So what is a heap exactly? Well, a heap is just a binary tree which satisfies a few properties. Now there are two types of heaps that we have. We have min heaps and we have max heaps. Now min heaps and max heaps are quite similar, but they have a fundamental difference between them, and that's just the relationship between the parent and child nodes. So to explain this in more detail, if you look at a min heap, it has to satisfy a property that is each parent node must be smaller than or equal to its child nodes. So let's say I've got this binary tree right here. I've got a parent node of 5 and I've got two child nodes which have values of 10 and 8. This satisfies the min-heap property. Why? 5 is the smallest out of the three. So the parent node 5 is smaller than 10 and 8, both the child nodes. Therefore, it's a min-heap. And if I was to add a subtree into this binary tree, so here I've got 12 and 10 as the children of the node 10. This still is a min-heap, right? Because 10 has, or rather I'll say the node 2 with index 2 has the two children 12 and 10, and the smallest child node there is 10, and 10, 10, they're equal, right? So we still satisfy the min-heap property. What about max heaps? And with a max heap, each parent node is greater than or equal to the child nodes. So just flip a min heap on its head and we basically get the requirements for a max heap. So here, if I take another example, this is an example of a max heap, right? So the first node 15 is greater than 7 and 11. If you look at the node with index 2, which is 7, it's also the greatest value because 7 and 7 are equal, so it still satisfies the max heap property. Now let's look at this tree specifically because this is another thing about heaps which is not often talked about and can kind of throw you off if you don't understand it. If I was to remove the third layer of nodes, right, 7 and 3, if I was to move them from node 7 to node 11 and I made the subtree go to the right instead of the left, do you think this is still a max heap, or rather it satisfies the properties for a heap? The answer is no. And this might be counterintuitive for a lot of you because you might be thinking, well, technically it does satisfy the max heap property because 11 is greater than 7 and 3, and 15 is greater than 7 and 11, so the parent nodes are the maximums. But there's one more property which applies to both min and max heaps that I haven't talked about, and that property is the tree must be a complete binary tree. Regardless if we're doing a min heap or a max heap, it must satisfy this property. You might be asking, well, what is a complete binary tree? And that's a good question. A complete binary tree is a binary tree where all of the levels, except the last one potentially, are fully filled. However, the last level can be fully filled, but if it's not fully filled, it has to be filled from the left. What that basically means is I can have this 7 and 3, the third level, I can have subtrees for 7 and 11, but I can't have a subtree just for 11, right? So the left side has to be full for it to be a complete binary tree, or it can be the left and right, but it can't just be the right. So that's an important thing you have to keep in mind, because if you don't have a complete binary tree, a lot of the algorithms which you apply on the heaps will no longer work because they have this underlying assumption. So you might be thinking, okay, well, how can I use this algorithm, right? Well, let's say I've got an array of that's 8 elements, right? So I've got this array of 8 elements. How can I turn this into a heap, right? Well, the first step, we've got an algorithm for turning this array into a binary tree in place. And there are other algorithms like the top-down approach, but the bottom-up approach is usually the one we use the most because it's quite fast. So, how do we use this algorithm? The first step is we have to turn this array into a binary tree, and that's pretty simple. All we have to do is take a node, and the next two nodes after it represent the left and right node respectively. So I will take the first node, which is 1, and the left node is 15, and the right node it's going to have is 5, right? So 1's the parent node, 15 and 5 are the child nodes. And I'll just draw some edges right there. How about the next two elements, 12 and 13? Well, 12 and 13 will be the child nodes for 15, right? And then as you can probably guess, 4 and 7 will be the child nodes for 5. So just count 2 across to be able to get the child nodes, right? So 4 and 7. And then we've got 8, that's going to be the child node of 12 right there. So that's the last node that we have. So this is a binary tree representation of this array. Now, how can we turn this tree into a heap? Well, the first thing I'm going to do is that I'm going to give each of the elements in this array an index, and I'm going to start at index 1 instead of 0. So in programming, usually we index arrays from 0. However, I'm going to be indexing them from 1 for now, and you'll understand why I'm doing this in a minute, but it's important that we use 1. So I'll just label all the indexes these nodes have right here. And if I just make some space on the left of the screen, I want to show you guys a couple interesting things. If I take a node, let's say 1, and I times it by 2, right? So n represents the current index we're at. So 1 times 2 is going to give us, if we add 2 rather to it, we're going to get 3, right? So 1 plus 2 should give us 3, and that's the index 3. So if you times by 2, we get the right node. However, if you do the same thing, but we minus 1 from it, we get the left node. So what we can basically do is take pretty much any node in this array, or any index, and if we apply these two transformations to it, we're able to get the indexes of the left and right node if that index exists, right? So if you try this on element 8, for example, that's going to be indexed out of bounds, so we know that it is just a leaf node. It does not have any children. Now, I can write down those formulas up there. So left node is times 2, the right node is times 2 minus 1. Now, if I want to get, let's say, the parent node, I can do this formula. So I take the index of the element I want to find the parent node of, I just divide it by 2, and then I floor that, which basically means I round that index down. So if I got, let's say, index 4, for example, which has a value of 12, I divide that by 2, then I end up getting a value of 2, which is the parent node, 15. Let's say I take an odd number, for example, 7. I do 7 divided by 2, I get 3.5. I floor that, so I round down, I get index 3. And as you can see, the node at index 3, 5 is a parent node of the node at index 7, which has a value 7. So these are useful formulas which we're going to use when we're actually writing the bottom-up algorithm. Now, another thing we can notice is that we can calculate the indexes, or rather the range of indexes of all the parent nodes with this formula. So I'll take all of the nodes, or rather the maximum index in the array, so in this case is 8, and I divide that by 2, which gives me 4. What that basically means is the nodes with indexes 1 to 4 are parent nodes, or rather these are nodes which have children. So if I highlight this right now, so 1, 2, 3, 4, these nodes have children, right? They have child nodes. And nodes with indexes 8, 5, 6, and 7, they're leaves because they don't have any children. And this is important because we need to know which nodes have child nodes, because we're going to have to run an algorithm, the bottom-up algorithm on them. So how does the bottom-up algorithm actually work? Well, we go through each of the parent nodes in reverse order. So you go from 4, 3, 2, and 1, and then we heapify each one recursively. Now, what does heapify mean? You might be asking. Well, heapify is a important algorithm, or rather just a simple process we can use to change the order of these nodes in order to get them to fit a certain property. So let's say I want to calculate a min-heap, right? And I've got this subtree right here, 15, 12, and 3. I give them indexes 1, 2, and 3, right? So I got an array here. What we do with heapify is we take the parent node, in this case 15, and we compare it with the child nodes 12 and 3, and depending upon if we're doing a max heap or a min heap, we might flip the order of some of these nodes or the values they have. So if we're doing a max heap, we have to satisfy the property that 15 must be the greatest, or rather the parent node must have the greatest value in the subtree, right? So the value of the parent node must be greater than or equal to the value of the child nodes. If we're doing a min heap, on the other hand, the value of the parent node must be less than or equal to the smallest value of the child nodes. So in this case, let's say we're doing a min heap, we can say that 3 is the smallest child node, or rather the smallest child node, and is smaller than 15. So we just swap these two, and that's heapify, right? We just satisfied that property. Let's say I've got another subtree, right? I've got 2 and 4 underneath it. So I swapped 3 and 15, and the thing about heapify is we do it recursively. So then we take the value we just flipped, and then if it has a subtree, we run the operation again. So if I do something, let's say I heapify a node which is level 2 of a subtree, and I've got 12 levels, we recursively do it so it goes all the way down. So we satisfy all the subtrees in that path. So here, let's say I've got 15 now, and I've got 2 and 4, and I'll give them indexes 4 and 5, right? So this is another subtree underneath it. I can heapify again. So in this case, 2 is the smallest child node. So then I swap 2 and 15, and then we heapified it again. So as we have more and more levels, we can recursively heapify them down and down. So let's go back to the original example we had, right, of this binary tree. We're going to start off at the last index, which the last parent node, which in this case has index 4, right? So it has value 12, has index 4. Now it has one child node which is 8, and 8 is smaller than 12. So if we're trying to make a min heap in this example, then we just flip those two, right? So we do 12 and 8. And of course, if we're doing a max heap, that'll be fine because 12 is greater than 8. So we just flip that check that we do. So min heap, we check if it's smaller than or equal to, and with a max heap, we check if it's greater than or equal to. So now that we've flipped 8 and 12, we check if index 8 has any children. It does not, which means it's a leaf, so we can just stop the heapify operation there. And then we just move on to the next parent node, right? So in this case, that's going to be 3. Or rather, we can do 2 as well. So we flip 2, so we have 15 and 3. We just swap those two. And now we can check if 15 has any child nodes. No, so it's a leaf. We continue to the next index, which is 3. So 3, we have the 2 children, 4 and 7. I swap it with 4 because that's smaller, right? And now 5 has index 6, and 6 is a leaf node, so we just continue on to 1. And in this case, 1 is smaller than 3 and 4, so we can just leave it there. And if you look at the tree now, it actually satisfies the min-heap property. So I'm going to be showing you guys how we can write this bottom-up algorithm. So before we write the heap implementation in C, I want to show you guys a school community I made. So in the school community, we currently have a pre-sale, because I'm still creating all the courses. But in this pre-sale, you can get the school community for half price, which is $30 a lifetime. And you know, in this community, we're going to have access to weekly Q&As. You can ask me questions directly. I'm releasing new courses on C, memory management, data structures, algorithms. We can create portfolio level projects. I'll walk you through each step of the way. And yeah, I'll leave a link to the description if you guys are interested. And if you watched this far in the video, you clearly seem to be interested in investing in your own education. So yeah, check it out. So right here, I've just got a simple hello world program, or not really hello world. I've got this array I've made right here, which contains 10 elements. And then I wrote a comment right here to show you guys the indexes of the different elements. I've also included a bunch of libraries, which we're going to need, or the header files. And then I've also got this heap print header file. So I'll just quickly show you guys. Heap print has this macro called array count, and this just tells us the size of the unordered array, or rather any array on the stack. So if I do something like printf, let's say array count unordered array, right? That should be LD. That's going to give me 10, right? That's the maximum size of this array. So if I change this to 15, right, and I do that, it's going to give us 15. Just allows us to see the maximum size of this array. And then I have another function right here called print heap, and that just prints out the heap for us as a string. So I can just do print heap unordered array, and then the count we can just get from array count unordered array. We could also just put 10 in here, but if we just change the size of the array and we add some elements to it, then we have to change with the values. So just easier to use macro because it calculates it for us. So if I just print this out, let's do this first. So as you can see, it might be a bit small actually, so I'll make this a bit bigger. So here I've got the root node, which is 5, then 10, 15, the child nodes 19, 98 and 4, 13 and 5, then 61 and 49, which is the child nodes in 98, and then 2. So it's a bit awkward, the printing for it, but hopefully you guys can understand that where the parent child nodes are, because this makes it easier for us to visualize the algorithm in action. So the first thing we have to do is actually write a function for heapify bottom up, right? The actual algorithm. So say heapify bottom up. We're going to take in a pointer to an array, which is going to be our heap, or the binary tree, which we're going to heapify. And then we're going to turn it into a heap. And then we're going to take in a count, which is basically how many elements does it have. And then we have a max. And actually I'm going to rename this. I'm just going to say max or min. It turns into boolean. Max or min just tells us, are we trying to create a maximum heap or a min heap? And this will let us know if we're supposed to do a greater than equal to comparison or less than equal to comparison when heapifying a subtree, right? So the first thing we have to do is calculate the range of values, or the range of indexes of parent nodes. And if you remember, I told you guys about that formula we had before. So I can just do count divided by 2, and that will just tell me the last parent node index. And since we start indexing from 1, because we need it for the parent and child, or the left and right node formulas, I'll get into that in a minute. But since we're counting indexes from 1, we set a range of 1 to this value, and that's going to give us an interval of all the indexes of parent nodes. So I can say int last parent node index is equal to count divided by 2, right? And then I can just loop over all of them in reversed order. Last parent node index, I is greater than 0. So basically is 1 to last node index, and then we do I minus minus. Right, then I just run this heapify function. I pass in heap, I pass in the current index, and then I pass in count and max or min. Right? So let's write heapify. So heapify int pointer heap okay. So the first thing we have to do is I'm gonna add some conditions to make sure the index we're trying to access is valid, right? So there should be a comma. So if the index is greater than count, or the index is less than 1, then we know it's an invalid index, so we can just return early, right? Similarly, if we have an index which is greater than count divided by 2, we know we should return, because then we're accessing leaf nodes, and we don't have to access leaf nodes, right? So basically this function is going to be recursive. So if we access a node which is a leaf node, we want to return because we can't actually heapify anymore. There's no more subtrees underneath it. So we just have this statement to check if it's a parent node. If it's not, we're going to return early. So first I'm going to get the indexes of the left and right subtrees, or the left and right nodes of this subtree. So I say right node is equal to 2 times index plus 1, right? And in the PowerPoint presentation, I actually had the wrong formulas. It should have been a plus instead of a minus. Some of you guys might have caught up on that. But we're going to do plus 1 right here. And then this will just give us the indexes of the left and right nodes of the current parent node. And this is why I'm indexing from 1, because if we try doing, if you have an index of 0, and we do 2 times 0, for example, we're going to get 0. So we won't get the values for the left and right subtrees at the first level, right? So that's why I'm doing that. Then I have this function, I have this variable right here, which is called swap, and I set it to index. This basically lets us keep track of what value is the largest or smallest inside of the subtree, or rather the index of that node. And if the index of that node, after some comparisons, ends up not being the parent node, then we know we have to swap it, and then we have to call heapify again on the new position of that node, right? So the first thing I want to do is check if our left node is less than count plus 1, right? Because we might have some out of bounds errors. And then if we have max or min, so I'm just going to say, not here. Actually, I do it right here instead. So if max or min equals true, then we're doing a max heap, right? And if it's equal to false, we're doing a min heap, right? This makes it easier for us to keep track of which one it is. So say if max or min, so in this case if it's true, then we're going to be making a max heap. I can just say if the heap's left node minus 1 is greater than current node. So that basically what I'm doing here is actually, I'll quickly just finish off this function. If the left node, right, so the left child node is greater than the current node, so the parent node, then we'll say that the left node has the index of the left node is the greatest in the subtree, or rather the left node has the greatest value in the subtree, right? And the thing is, the reason I'm doing minus 1 here instead of just doing left node is because we're treating this index from 1 instead, right? So if we want to actually index it into the array, we have to minus 1 to get it to start from 0. So we just do that. And then let's say if we are doing min instead of max, right? So in this case we're handling the max case, otherwise we're doing a min, so we just swap this around, right? And then we can actually do the same, pretty much copy the code for the right subtree. So if I just copy this code right here, and instead of doing left node, I do right node, right? So this is just checking if the left subtree is, if you have to swap with the left node in the subtree, and this checks if they swap with the right node in the subtree, right? And then we also handle the case if we're doing a maximum or minimum heap right here. So we'll just check if the swap index is not equal to the current index. This means that either the left or right node is satisfy the property to justify a swap. So let's say if we're doing a max heap, that means the left or right node is going to have a greater value than the parent node. If we're doing a min heap, it's the opposite. So the left or right node has a smaller value than the parent node. So we have to swap it. So we can just say something like temp. We're just going to temporarily store the value of index, right, in this temp variable. Then we'll say heap at index minus 1 is equal to heap at int swap minus 1. So basically saying is that the value of the node which you're going to swap with, we're just going to swap with the parent node, and then the original value of the swap node, we're just going to set that to temp, right? So basically it's done here. Let's say I'm making a min heap, and I've got 5, right? Then I have 3, and then I have 4, right? So I'm just let's say in this case we're going to make a min heap, then 3 is going to we have to swap 3 and 5 because 3 is smaller than 5, right? So what we're going to have to do is we're going to store the value of parent node, which is 5, in this temp variable. Then I make 3 the parent node, and then I make this original the left node, I give it a value of 5, which is stored in temp, right? So swapping it. Now that we've swapped it, we're gonna have to call the heapify function again because it's recursive. Because let's say I've got another tree right here, it's like 1 and 3, and then I have to call heapify to make sure that this is the smallest one, and if it's not, in this case it's not, I have to run heapify and then swap them all again, right? So that's basically how it's going to look like. So we're going to call heapify on the new position or the new index of our parent node. So say swap count and max, right? So if I actually run this quickly, so let's say heapify bottom up, pass in heap, and I pass in count. That's going to be array count, unordered array. And then I do, let's say, let's make it a max 1 for now. I did not include std.h. Let's get that in. Okay, so let's compile the code. Missing, let's see, 51. Okay, I'm to remove this. Max undeclared identifier. Where's that? That should be max or min. So as you can see, actually it might be hard to understand this way, so I'll just do printf before, right, then we do printf after. Okay, so you can see before this is the subtree, the binary tree we had 5, 10, 15, 98, 4, blah blah blah. Then we do a max heap. So we do bottom up, we're trying to create a max heap. So here we've got 98, 61, 15, right? That's a max heap. 49, 4, great, 10, 5, 2, 3, 15. So we just turned it into a max heap, right? If you want to turn it into a min heap, you can just set this variable to false, and this will just turn it into a min heap. So as you can see, it's our the smallest of the subtree, right? Let me just go down. As you can see, it's a min heap. So I hope you guys enjoyed the video. I hope it was informative. If you got any questions about the algorithms, or maybe you feel like I didn't explain something properly, or you didn't really get what I'm trying to say, then please leave a comment. I'll be happy to answer any of the questions you have. Of course, the code is in the description below. It's on my GitHub. And I will see you guys later. I've also got a video about dictionaries in C and how we can use them. You might find that to be interesting as well if you watch this video. So thank you for watching, and I'll see you guys later. Bye.